So we know that Internet of Things is a platform to which many devices can be connected over the internet. But in the communication, especially when this Internet of Things are being deployed for the 4G, 4GLT in the next generation, 5th G in the 5th generation mobile phone, the intensive the smartness is coming through the Internet of Things. So we need to understand what the smart antennas are used and how it is used for, especially for the Internet of Things. So when smart antennas are deployed for the Internet of Things, they can do this with no changes. They can definitely improve the IoT network performance, and they can do this with no changes to the population of the wireless IoT devices. Only the IoT gateway terminal, usually relative a few in number, need the upgrade. But ultimately, everyone reaps benefits: network operation from improved coverage, data capacity, network improvement, location services, and network users from lower cost and lower power of IoT devices. So these IoT networks, in contrast, typically still rely on antennas with fixed radiation characteristics, means which fundamentally limits the operation distance and the data rates of individual radio links and the capacity of the overall network. Therefore, the smart antenna is a transformational, and the smart antenna is now emerged as a very important component and instrumental in communication, especially when it is deployed for the Internet of Things. It will do a wonder. So let us see what is a smart antenna. Is basically a smart antenna is basically consists of, as I told in the beginning, it consists of a phased array antennas or the array of antennas which can quickly control the digital signal processors. So these smart antennas are they able to they control their own radiation pattern. They can adapt them. And so sometimes it is termed as it's a self-configured or self-intelligent, etc. So the smart antennas are used for solving the plethora of problems which are there for the wireless communication in terms of digital signal processing, DO estimation, or beamforming, etc. So when we see this particular diagram, in this particular the diagram, we can see that how this smart antenna can be used for Internet of Thing application. So in this example, we have considered a 4-element antenna array, and this element antenna array are passed through the amplifiers and transceivers, and their digital signal processors are there. So this digital signal processing, the entire smart antenna system is two-way, and it is controlled by IoT gateway. And this way, we can say that the smart antenna can radially improve the IoT network performance. This is a wonderful thing. That is a wonderful part of this smart antennas. Next thing, this diagram. So we know that when smart antennas are used, the smart antennas are very intelligent. They can produce a beam, the required beam, the user beam, in the particular direction where it is required. And at the same time, it has an ability to discard the nulls, or it has an ability to discard the interferences. So in the figure 2, it has been demonstrated that the main beam is pointing towards the user, and some red colored one is the interferences which might be coming from the IoT devices or other mobile phones or any from. When IoT gate terminals are used, intelligently the smart antenna can reject the interferences and places the nulls in the not interested direction, and only the main beam in the direction of user. So now let us understand the basic architecture. Then what so many applications and so many the things which we have explained in the figure 2. In addition to that, there's a few more points I would like to cover for system with mobile devices. The direction of each beam and the position of nulls adapt to the changing direction of all devices. Means this also protect against the interferences from neighboring and overlapping networks as the destiny of IoT deployment grows. This example illustrates that how the modest smart antenna system can increase the capacity of an IoT system, and by the factor up to the greater improvement possible. Means the performance can improve up to 4 times when smart antennas are used for the Internet of Things. So for example, for the Internet of Things, classical antennas are used, we could see the decline in the performance. So with this advantage of a smart antennas for the Internet of Things, it is the time to understand and detail what are the smart antennas and what are the insights of the smart antennas, so that these are useful for not only mobile communication, satellite, radar, sonar, navigation, also for the Internet of Things in order to improve the capacity of this IoT networks and many things. So this is an architecture where in the figure A of 3A and 3B that's shown. One is a phased array where a phased array system has no control over its radiation pattern, means digital signal processor is not that. This is a classical array antenna. At the same time, we can see in the figure B, the phased array antennas are completely controlled by the radiation, with the algorithm, digital signal processor, the block diagram, which is shown at the end of the diagram, DOA or adaptive beamforming algorithm. So these algorithms are completely controlling the radiation pattern of an antenna so that they can place the user direction. They can place the user direction in the desired one, and they can suppress the nulls and they can reject the interferences effectively. So in detail, when we see the diagram of or the architecture of smart antenna system, let us consider when we are having multiple antennas are there, more than 100 antennas or more than 64 antennas, etc. For example, when we consider 4G LTE system, there are 4G LTE system, multiple input, multiple antennas are there, maybe 4 and 4 is 4 into 4 matrix. But in the fifth generation, which will come very soon, for the fifth generation mobile phone, 64 and 64 or 120, 120 massive MIMO when it is there. So when the signals are received, they are immediately converted into baseband signals. Then there are the super converters called analog to digital. These digital signals are given to the phase shifters. These phase shifters are adapted intelligently by the digital signal processor so that it will produce the output in the desired direction. So how it works for the 5G and many things. And I will be covering in more insights on how it is useful for the Internet of Things and what are the challenges are there for the Internet of Things when it is used for the 5G, and how 5G mobile phone is full of smartness in controlling the cars, controlling the AC, and controlling the many aspects through the IoT. That and what are the technical aspects and how smart antennas play a role for these things will be covered in the due period. Okay, next one. So in the figure 5, it is shown it is shown that that is a small animation where the phase shifters are producing a beam in the required direction. And in the figure B, we could see that the blue and red colored one. So where the blue and red colored one, the blue one, the figure 6 in the blue colors represents the direction of intended signal, and the red one are representing the interferences signal. Interferences signal. So now, what are the digital signal processing aspects? So when we see the digital signal processing aspects of the smart antenna, so antennas are becoming smart only because of the digital signal processing parts of this thing. So one is the direction of arrival. So one is the DO, means direction of arrival, where estimating the direction of all the incoming signals very accurately, that happens in the radar. Then next one is the adaptive beamforming. This one is very important, through which the incoming signal, the required signal of interest is placed in the desired direction, and the other signals are simply discarded. And the radiation pattern optimization, calculating precisely what is the signal of interest and signal of not interest. So with this, we can now we can go to the what are the benefits of or the needs of a smart antenna. When the smart antennas are used, one of the important concept is a space division multiple axis. It suppresses the clutters, it provides the wide bandwidth, improves the capacity, improves the frequency range, and suppresses the side lobe, etc. These are the important aspects of the features of smart antenna system. Now let us go into the algorithm, because I'm going more into the smart antennas because the smart antennas, when used for the Internet of Things, they are doing wonders, particularly in the 5G mobile communication. For example, in the 5G mobile communication, the brightness of the mobile phone can be automatically corrected, and many things. Not only this, for example, the cars can be tracked. When the person is in the car, that can be tracked simultaneously to the direction of arrivals. So beam will be formed in a particular direction where it is required. So many applications we could find in the 5G, and when IETs are used deployed exclusively for the 5G through the smart antennas, many features are controlled. So we need to understand in detail what is a smart antennas and how it can be used for the IoTs in the last sites. So basically, when speaking the algorithms for the smart antennas, there are the two algorithms are there for the smart antennas. One is adaptive beamforming algorithm. Another is direction of arrival algorithm. So adaptive beamforming algorithms are the algorithms which adapts their beam and steers the beam from any direction. When linear arrays are used, it will steer from -90 to +90. When other circular arrays are used, it will steer the beams from 360 degrees. So direction of arrival algorithms means that they estimate precisely the incoming signals directions, which is also very useful for the IoT, Internet of Things. So, for example, when person is in the car and he is going to home, and in the home, the AC should be turned on and it should be adjusted to the required room temperature. Means the continuously the tracking of a person and coming towards its home is very much important when it is connected through the IoT, to Internet of Things. So Internet of Things should turn on the AC and should go to the required the temperature, and how it is possible to track the person, and through the person mobile phone means the direction of arrival. The accuracy of direction of arrivals are very important for these things. Now, generally speaking, what are the adaptive beamforming algorithms? There are many algorithms are there for adaptive beamforming algorithms, which are the important aspects of the smart antenna system. Smart antennas are becoming smart because of these algorithms, which are studied from many days, and improvements are studying in the literature. One is the least mean square algorithm, and the improved versions are normalized mean square algorithm, robust algorithm, conjugate gradient algorithm, recursive least square algorithms, hybrid algorithms are there, and many things. So towards the direction of arrival methods, there are plenty of algorithms are there they can use, like multiple signal, root music, unitary music, and estimation of signal parameters via rotational invariance techniques, Capon method, Minom methods. These are the methods which are already there in the literature, and such type of algorithms are making antennas to precisely estimate the direction of arrival. And still today also many researchers for these are the favorite topics, and they are doing improvement, and continuously they are working on these direction of arrival algorithms. So let us understand in detail for the interested audience to understand the signal model of a smart antenna system, because it is very important. As far as the research is concerned, signal model, mathematical model, simulation models are very, very important. And we should understand firstly what are the smart antennas and how they can be used for mobile communication, Internet of Things, radar, navigation, tracking, sonar, etc. When we understood all these things for the research, the actual research, when it comes into picture, understanding of signal model, mathematical model is also very, very important thing. Now, when we see the signal model, this is very important for the beginners. It will be very, very helpful to understand how the diagram is there and how we can develop a mathematical model of any smart antenna system. When we say smart antenna systems and array signal processing concept, and the array signal processing concept, the antennas are phased array antennas or the MIMO antennas, which we are using, are the very important thing. And how we are using them, how the alignment we are making. When we see that the alignment shown on the horizontal, that is called uniform linear array antennas. These uniform linear array antennas are precisely located at the distance of d is equal to lambda by 2. Why d is equal to lambda by 2, where d is the distance between two antennas and lambda is the wavelength between the wavelength of a radio signal? Because we have two things which all know in the communication system. One is mutual coupling, another is a grating globe problem. So when antennas are brought very close below the lambda by 2 means a mutual coupling problem will encounter, and when greater than lambda by 2 means grating lobe means an extra lobe in addition to the main lobe will appear in the radiation pattern, so that it has an ambiguity to IoT, so that IoT will be in a confusion. And for an IoT or for a radar or for a mobile communication, it will be very difficult to identify which is a user direction, and the tracking will become a difficult because of the ambiguity that is produced by an extra or an unwanted beam which produced in addition to the main lobe. Now let us go to the introduction of the direction of arrival estimation mathematical model. Now, to understand the mathematical model of a direction of arrival, these are the key parameters which we need to understand. The key parameters or the vectors which are very important and is instrumental in developing the signal model is the steering vector, spatial covariance matrix, signal line noise subspace, autocorrelation, cross correlation, norm vector variance, and eigenvalue vectors, etc. Now, and when we see the equation, development of equations or formulation is concerned for an array data matrix, when we receive, for example, in equation 1, the received signal is taken x of n is equal to I is equal to m minus 1, where m is the antenna, number of antennas. The S of n is the digital signal, which is a desired signal, and A of theta is the steering vector. The steering vector is responsible for steering the beam from one direction to the other direction. And equation 1 and equation 2 are basically, they are the one and the same, but in equation 2 represent the matrix form of equation number 1. Now, more precisely, in equation number 3, we could see that how the steering vectors are taken for all the signals. For example, there are L number of signals are coming. For all the signals, a steering vector is required because the signal is coming from a different direction, and we can control the direction of incoming signal, or we can steer the incoming signal to a particular direction through the phased array output and through the steering vector. So for each incoming signal and for each interference, we are having a steering vector, which steering vectors are n minus 1, and they're nothing but, for example, we are having m antennas, L signals, m into L steering vectors are there, and for the desired signal plus noise. So noise is usually we take consider as a auditive Gaussian noise for most of the application, but there are also colored noise are also there in a communication system. Now, when we see this particular taking the array output for a beam forming technique, so for the beam forming technique, the output of a beam is very very important, which produces in a desired direction, which is which explains us or which gives an idea where the intended signal or desired signal or user is there. So array output y of t is equal to, it is the weights multiplied by incoming signal. We usually take the Hermitian transforms of the weights. These weights are nothing but from the phase shifters into the input signal x of n, that is in the previous slide equation number 1. So that is it. Again, we can express it, that is the x of n is below a steering vector desired signal plus interferences and the noises. So array output is a beam that can be steered in any direction. Now, some of the important adaptive beamforming algorithms when we consider, which already told in the introduction part, are the least mean square, sample inversion matrix, recursive least square, CGM methods, etc. are the popular adaptive algorithms which are available in the literature. Now, as far as advanced adaptive beamforming algorithm are concerned, which I worked in my research, my doctoral degree and a postdoctoral one, a few algorithms have been developed, and I would like to focus on those algorithms and how useful these algorithms for the Internet of Things, improving the Internet of Things networks, etc., and making the rejections of interferences in Internet of Things. All these things can be discussed in the two slides. Now, firstly, we have developed the first algorithm called as the variable step size normalized least mean square algorithm. So, already LMS algorithm, least mean square algorithm is existing in the literature, and normalized means one is already existing in the literature. However, if they are having their own downsides, for example, the mean square error which is there between the user signal and the desired signal, that to reduce that lot of iterations, the is required for algorithm. More than 100 iterations are required for LMS and NLMS algorithm. That is a very time consuming and a tedious one. In order to overcome that particular thing, we have used, we have improved the variable step size algorithm. So we call it as a variable step size normalized algorithm through the equations which we have presented. Now, as far as the results are concerned, when we consider the smart antenna performance for IoT, so what is the IoT Internet of Things? They are configured for many things for to make a smart ecosystems on a single platform on internet. Many devices are controlled, particularly in 5G. The challenge is more because for 5G gives a large bandwidth. When it gives a large bandwidth, the data transmission is high for video audio, and many number of components can be integrated and can be collaborated, can be controlled. So for that, the robust beamformers are required. Smart antennas are indeed the very important component for the Internet of Things because communication takes place through the devices, through the antennas. When antennas are smart, when the antennas are robust, when antennas are capable for tracking and forming a beam in a particular direction efficiently, it makes the system more efficient one. So smart antennas are actually the solutions. Actually, the actual solution for the 5G is the smart antennas because it gives the large the required bandwidth without expecting the large cost. Interferences can be removed, can be mitigated, nulls can be minimized, so robustness can be brought. The communication device work in severe signal to noise ratio conditions. Clutters can be removed, faders can be removed, coherent signals can be resolved. So these are the plenty of advantages of a smart antennas when deployed for the 5G. And in the 5G, the use the concept of IoT is more as compared to the 4G LTE and 4G, etc. In that point of view, the development of an algorithm, not only for the point of the IoT, so this is actually from the point of communication system improvement, performance improvement of the communication devices. So we have developed the algorithm is successful in many scenarios and many situations. We can understand how iterations are brought down from 100 to 18 in a figure 2. And in figure 1, the radiation pattern is so highly directive, pointing towards the user direction. If you assume user direction in the 0 degree, it is pointing towards a 0 degree very effectively. So as far as the number of iterations are concerned, the net number of iterations are very quickly fallen down, and in less iterations, the algorithm is producing the required beam. Now, as far as the steering, beam steering is concerned, when you use the uniform linear array, we actually you can see in the figure the beams are rotated from many degrees, from 0 30 degrees, from 0 to 40 degrees. So in minus 90 to plus 90 in all directions, the beams have been steered. Now, another the things which we have developed is the development of 2D Nova uniform linear array. The existing uniform linear array are not precisely estimating the direction of arrival, particularly end fires, means at the ends of the uniform linear array. For example, at the ends, the signals are coming into direction of arrival. Algorithms are deteriorating in performance to estimate the required one. So from that point of view, we developed this doubly crossed uniform linear array. We called it as 2D uniform linear array. So the mathematical model for the so those who are interested, you can look into the equations, how we have developed the equations. So each and every signal, for we have taken for a horizontal component and a vertical component. We have taken a steering vector incoming signal for a horizontal component and a vertical component, etc. Finally, we determined the array factor for horizontal, determined the array factor for the vertical component. So the simulation result, this is the best part of our work, and the best part of the work is always simulating result and validating and understanding how the improvement it has, the algorithm is giving over the previous ones. So when we look into these things, the beam when these things, the pink colored one, the magenta color simulation results are superior as compared to the blue colored one, which are obtained for the normal uniform linear array. When two-dimensional uniform linear arrays are used, the performance is more, null depths are more, interference rejection capability is more as compared to the uniform linear array configuration. So this same thing is formed in a tabular form to illustrate how interference nulls are gone down, and so that the immunity of our the robustness of algorithms are more. Now, through these are the questions. No, we'll go to the next one. So after that, now because of a time limitation, the plenty of things has to be covered in the session 9 to 10, morning 10. So let us go to the direction of arrival estimation. This is the second part of the smart antenna system. So newcomers or researchers or professors who are interested in asking the questions on beamforming, please feel free for the discussion on the beamforming particularly for 5G or IoT, etc., so that I can proceed for the direction of arrival estimation. If no doubts or no interaction, then I can proceed for the direction of arrival estimation. Okay. So direction of arrival estimation methods, the very first algorithm is the music algorithm, which has, this is nothing but multiple signal classification algorithm. Now we have the multiple signal classification algorithm. This algorithm was first presented by Arrowsmith in 1986. Today also, this is a favorite algorithm for many applications and many developments, 5G and for many other things. So this algorithm has its own problem. because the algorithm has an not ability of solving the coherent signals completely. However, the music algorithm partially can resolve the coherent signals, but the effective resolving the coherent signal is indeed the challenging aspect of the communication system. So this is because of this, when used in a signal to noise ratio, which is in where noise is more, also this music algorithm deviates in performance. Right? So how this music algorithm or any direction of our algorithm works? The first one we need to understand that the calculation of coherence matrix eigenvalue decomposition. Here eigenvalues and eigenvectors. So eigenvalues and eigenvectors respectively for the representing for the noise and the signal space. So this will take into the two parts, so signal space and the noise space. In the music spectrum, the pseudo spectrum is taken, and the universal pseudo spectrum is taken in order to find the largest peaks. So in the music algorithm or in the modified music algorithm is our work, which is very similar to the music algorithm, but we have used some our own mathematical concept in order to improve its performance, particularly for the coherent signals and particularly when the signal to noise ratio is very less. So we can see that that the modified that when the direction of arrival estimation presented in the first figure is for the coherent signal is deviated when the music algorithm is applied, whereas when modified algorithm used, if we assume that the four signals are there, required estimation minus 20, minus 10, 10, 20, our algorithms are definitely they are very precise in estimating the direction of arrival of all in presence of coherent signals also. So we can see that how the modified music algorithms are effectively working for multiple different antennas. When antennas are 3, 6, 10, and 15, they are producing the required one. However, then we can So we can note that every time the beam the directivity of beam is increasing for when the antennas are increased from m is equal to 3 and m equal to 15. The figure 4 is a very interesting figure where we are varying the d. D stands for distance between the two antennas. So it is already explained in the mathematical model, that signal model, that d should be precisely 0.5 lambda or lambda by 2. So if it is less than lambda by 2 means we could see that the mutual coupling effect will be there. And if the d is more than lambda by 2, for example, the black one, d is equal to lambda, we could see the multiple, the grating lobes which are not of intended direction are coming. So these are the grating lobes, which is an ambiguity for any device. So as far as the number of samples are concerned, then we have already studied this modified music algorithm for different samples, and even for a very few samples also, even for samples when we take 400, 500 samples, or even 200, 300 samples also, there is no change in the performance of the proposed music algorithm or the modified music algorithm. Now, when we consider the signal to noise ratio condition, figure 6 and 7 respectively illustrate that one, when the classical music completely deviates in performance for signal to noise ratio is minus 10 and minus 20, whereas the music algorithm, which is a modified music algorithm, is, uh, is, is, is giving accurate result even for all the signal to noise ratio and very less signal to noise ratio or 0, 20, 40 also they are giving the accurate results. So these are the outcomes. Now we can understand a few more points about this slide, where in the figure 6, when the classical music. So why I'm stressing more on the classical music, because these are the direction of arrival algorithms which are there in the smart antennas and which are used for the Internet of Things in order to localizing the things, in order to detecting the devices or detecting the direction of arrival, means how it is detection is possible, tracking and detection in positioning is possible only through the smart antenna algorithm, whether it is an IoT, whether it is a radar, where for this tracking, estimating, and all these things are possible. All these things are possible only through the smart antenna algorithms. Smart antenna algorithms like music algorithm is there, smart antenna algorithms like estimation of signal parameter where rotational invariance techniques are there, and its improved versions are there or modified versions are there. So here we would like to stress on more because this is the practical the situation where we could face the many challenges signal to noise ratio conditions. And the signal to noise ratio is 50, 30, 10, etc. We could see that the direction of arrivals are estimated accurately. That is, the direction of arrivals considered here are 20 and 60. For 20 and 60, direction of arrivals are the incoming signal. They are estimated accurately. But whereas when we go to the minus 10, when we go to the minus 20, we could see that the deviation has taken place. We could see multiple peaks are coming in the graph. It illustrates that the signals are precisely not estimated. In addition to the estimating the 20 and 60, many peaks are represented. These are the ripples which could find for the classical music. The classical music algorithm is not suitable for when the signal to noise ratio is very less. Signal ratio is very less as compared to the noise ratio. Whereas in the modified music algorithm, we modified the mathematical model of a music algorithm in such a way that we have included actually how it is possible, what are the significant contribution to the mathematical model is we have used canonical form or Jordian method we used in our mathematical model. We improved the mathematical model in such a way that the signal to noise ratio, even for a small signal to noise ratio, and signal to noise ratio is 0, signal to noise ratio is minus 10, minus 20 also, the algorithm, smart antenna algorithm for estimating the direction of incoming signal or users, when it is user direction is 20 and minus 20 and plus 20 in this example. So all the incoming signals for minus 20 and plus 20 are estimated precisely for even for minus 10 and minus 20 also. So what are the outcomes now? Not only this music algorithm, direction of arrival algorithms, especially this modified music algorithm. What are the remarks of this research work? The first one is the modified music algorithms is a high resolution one because we have incorporated Jordan canonical matrix for coherence matrix estimation, through which we can effectively estimate the eigenvalues and eigenvectors so that the noise and signal space and noise space can be effectively done so that through the pseudo spectrum the direction of arrivals can be accurately estimated. So this is possible through the include which for the first time we have incorporated Jordan canonical matrix for estimating the spatial coherence matrix in the music algorithm, so that we call it as a modified music algorithm, which definitely improves the resolution of an algorithm. This is the first point. Second one is the outcome of this work is it has an ability to detect very closely spaced signals even under low signal to noise ratio. This is another important thing. When the signals are when the narrowband signals, when the uncoherent or coherent narrowband signals are there, when they're closely associated, or means, for example, one signal is coming at 2 degree, another signal is coming at 5 degree. In such a situation also, our algorithm is able to produce a beam in the desired direction. So this is another advantage of the proposed method. The next one is the proposed method has a great potential to find the direction of arrival for small number of array using a small number of antenna elements on the small snapshot. It greatly reduces the computational complexity. Here we should note this important point. We have demonstrated here particularly this particular figure 3, where even we are having number of antennas are very less. Let us consider for a 6 also giving the same result, almost similar result, and for the n is equal to 15 also it is giving a similar result. When antennas are 6, antennas are 15, there is no the huge difference in estimating the signal. Actually, the signals are estimated in the same way when antennas are 6 or antennas are 15. So this is an important aspect. Also, another important thing which we have noted is even for the small number of samples, also the algorithm is producing or estimating the direction of arrival accurately. Means this is important thing in a for a communication device is that significantly computational complexity of algorithm can be brought down. Computational complexity is one of the important issues in a smart antenna system or any other communication system, because as a complexity increases, many controlling or it affects the accuracy or it affects the resolution of an algorithm, and it demands the high cost. So in order to keep the cost low, and keeping the low cost, and at the same time, meantime, and having an efficient communication system, when small number of antennas are used, small snapshots are used, this is the more advantageous part of the proposed method. The next one, the important remarks of that this method is makes communication system robust and suitable for practical application. Why the proposed method is suitable for a communication system? Why it is robust? Because the signal to noise ratio. In the previous slide, we have understood these are the previous the things. In the previous slide, we understood that in the severe noise area or environment also, our these algorithms are robust and they are immune to the noise. Another way you can say they are immune to the noise, and because of that, they are more practical oriented. They can be used in very practical applications, including 5G and etc. Another thing is that another important aspect is that this method cannot only we have said that the d is equal to exactly 0.5 lambda, but when we take d is equal to 0.45 lambda, also it is giving almost the required result. Now let us come to the IoT. Now these are the basics or the insights of direction of arrivals which we have studied. And already mentioned in the previous slides that this direction of arrival or locating or estimating the signal is important for the 5G or IoT devices. So in this figure 8, which is a continuation of the direction of arrival estimation, locating IoT Internet of Things terminals with high resolution triangulation has been presented here. So here it is an example of how smart antennas can be used to locate the devices with an IoT network is illustrated. So this is a very important point. Here, the multiple smart gateway are positioned. You can see in the figure, I would like to repeat this point, is very important. Multiple smart gateways are positioned at the edges of the coverage area, and each producing a high accurate estimate of device bearings. The gateways cooperate to triangulate the bearings, and hence they are locating the IoT devices. So this is an important aspect. Now this smart antenna technology, see, when particularly in IoT gateways, can thus significantly improve the performance, so and the connected devices and the IoT networks as a whole. Therefore, but without necessitating a modification to the population of the wireless IoT devices, a wireless devices gain in battery life, operating range, whilst in the IoT network benefits from the increasing capacity, improves the tolerance to interferences, reduced infrastructure costs, etc. Therefore, the smart antennas can also add valuable features such as accurately locating and tracking the positions of individual devices. These are the things. So now last 10 minutes, my session 9 to 10. Let us take a 10 minutes time for interaction.
Sir, I want to ask a question personally. Participants are, I
Yes,
don't.
please.
Sir, I want to know about the radiation pattern of smart antenna, sir.
Yes, it's a very nice question, sir. Uh, I will share this. Sir, this one is one of the radiation patterns that is produced by a smart antenna. So this is a radiation pattern where there is azimuth angle, which is there on a x-axis minus 80 degree to plus 80 degree. It is because we have taken antennas uniformly, linear antennas. Antennas are arranged horizontally. When it is arranged horizontally, means it will use only 180 coverage. Circular means 360-degree coverage. So here, actually, it is minus 90 to plus 90, means 180 degree. But however, the graph is since the signals are minus 60 range to 60 range, it is from minus 80 to plus 80. This is a plot. Now we have taken the signal strength on the y-axis. So here we could see the many the signals which are coming in different direction, where the green one here represents the signal of interest, which is pointing to a very particular direction. That is a beam pattern direction, beam forming direction for a user direction. Whereas there is a dotted red colored one, that is there is an interference. So IoT terminal, when smart antennas are connected to IoT terminals for many smart ecosystems to controlling over a single platform, so interferences should be discarded and only the signal of interest should be taken. So this is how through the radiation pattern. This is one. But more detailed the radiation pattern is through our simulated result, where I can explain this one in a better way through this one. So this is the you can see the radiation pattern figure 1. Here in this radiation pattern for least mean square algorithm, LMS algorithm, that is NLMS algorithm, and variable step size algorithm. Here in the radiation pattern, the one will be a main lobe. Always this main lobe is towards the user direction. In this simulation, we assumed that there are some 10 antennas are there, and this 10 antennas signal of interest or user direction is 0 degree. So when the user direction is in the 0 degree, all the algorithms have produced the main beam in the 0 degree only. Whereas there are some other lobes, there are small lobes, we can say from minus 20 to minus 80 side, plus 20 to 80 side. They are called minor lobes or the side lobes. The side lobes are of non-interested. So the smart antenna, in the smart antenna, if the number of antennas are increased, for example, 10 antennas are replaced by some 64 antennas which are for 5G, automatically these side lobes will disappear. Only one major lobe will appear in the user direction. However, it is also possible that the beam, for example, when we pick a call and we will move from one position to another position, the beam will follow. That is called beam steering technology. So similar way, the user as user moves, the beam also moves. That is called beam direction changing, beam steering, and this is possible from beam can steer from 0 degree to any degree. Here we have shown how the radiation pattern the beams are being steered in a very different direction. Sir. Thank you, sir. Very good question. I think I cleared this one.
Yes, sir.
Dr.
Nice,
Vishwanath,
sir. Yes.
yes, sir.
Any participant wants to
Sir, I love to
any
interact. That is why 10 minutes I reserved the session for the interaction. I love to interact because only from one side I presented. And if any questions, please feel free for a discussion, sir.
please, participants, please ask your doubts, your questions towards the smart antennas. Sir, I think I have one more question.
Please, sir, please.
Yes, sir. Sir, actually, IoT consists mainly some use only mainly ISM band, industrial, scientific and medical band of 2.45
Yes,
gigahertz, in which the
yes,
Zigbee network and Wi-Fi network and other networks are there. So
yes, sir.
my question is, sir, is because all the data communication depends on the antenna transmission by the antenna and receiving by the antenna. Okay, sir.
Yes,
So
yes, sir.
there may be sometimes some interference in these networks, because suppose same time the wireless is enabled and as Zigbee devices also enables, and that time other ISM bands medical appliances are also enabled that time. So I think
Yes,
there
sir.
is an interference in the packet delivered by the transmitter and received by the receiver. Because
Yes,
IoT is a, sir, it is broadly, you know, that all there are the data transferring between all the heterogeneous devices
yes,
simultaneously.
sir. Yes,
So, sir,
yes, sir.
how can we make our smart antenna system so adaptable, so efficient, so that this interference can be minimized?
Yes, very nice question,
Is
sir. I
there
would like.
any software? Sir.
Yes, sir.
Okay, sir.
Yes,
Please, sir.
sir. I love to answer this question. Very nice question, because as you are being a very good researcher in IoT and many people, and we are in smart antennas for communication devices and IoT. So here, Internet of Things, the major challenge for the communication system, particularly
Yeah.
5G, where many number of IoT devices are connected, as you rightly pointed out, many interferences. For example, one with one device, another device is producing a signal, it will be interference. So I would like to answer this question with an example that, for example, what is the capability of a smart antenna? They are very intelligent. For example, in a real scenario, smart antennas are working in this way. For example, when I'm giving a talk, let us consider in a class, and I asked all my students to close their eyes. The students will close their eyes, and I will be giving a talk and moving from one point of the dais to the other point of the dais. So in addition to that, they will get this the noise from the fan. They will get the noise from the outside class. They will get the noise from other students which who are roaming outside the class. But the meantime, what the audience will do in the class, they will be focusing only on my words which I am delivering, though I'm moving from one point to other. But at the same time, when they are hearing the noise of the fan, noise of the other class, noise of the other teacher from the other class, they will simply discard. They will try their level best to focus only on the my voice. This is the physical interpretation. In the same way, smart antennas are such a way, the algorithms which are there, particularly a beamforming algorithm and direction of algorithm, which are available in the 21st century, they are such a way that their frequency matching to the IoT devices, which at the time, meantime, that is called the space division multiple access technique. Through the space division multiple access, they will, and this smart antenna algorithm, they will discard the other signal which it considered as an interference very intelligently, and at that particular time it will hop in such a way that it will take that devices for the giving a smart benefit for the user. This is for an answer for this particular question, sir. Thank you.
Sir, I want to ask one more question, if you have time. So,
Yes, please, sir. Please, sir.
sir, वो,
Please go ahead, sir.
yes, sir. I am asking, sir. I want to know about the beamformers, different types of beamformers in the smart antennas for the IoT devices.
Yes, sir.
Beamformers,
Yes,
yes.
yes, sir. So there are various beamformers are available in the literature, sir. So already this one, yes, this one. So these are the different beamformers, sir. First one is a least mean square algorithm. This is called LMS beamformer. Then it has a problem to overcome this one, LMS beamformer, then robust beamformer, then conjugate beamformer, recursively square beamformer, hybrid LS. It is a combination of LMS and RLS. This constant modulus beamformer, SMA beamformer, and plenty of beamformers are there. So these are the some popular beamformers which are taken from the literature, sir, and it improved versions. In our work in PhD and postdoc, we worked improved LMS algorithm, conjugate algorithm, as you have seen in one of the algorithm, variable step size least mean square algorithm, which is to solve the problem of LMS and NLMS algorithm. These are the efficient beamformers, sir.
More question from the Dharmesh Kumar from Babu Banarsi Das Institute of Technology and Management, Lucknow. He is asking, ki, sir, suggest the antenna for Arduino. Sir, Dharmesh sir, I think, oh, no, okay, sir will reply this answer because I am not so expert in this smart antennas.
Yes.
Sir, he is
Can I,
asking this,
can,
suggest the antenna for Arduino.
Sir, there are
Because,
many, sir. For example,
yes, sir,
there are
please.
many, sir. For example, it's antenna designing antenna. Antenna is just a radiating element, sir. Antenna is just
Yes, sir.
radiating element. So for the
Yes.
communication, for example, your Arduino is used for communication device. We suggest strongly a microstrip antenna, particularly square microstrip antenna, if it is. For example, if you want to go for a phased array antenna, radar and for array of antenna, these microstrip antenna, more microstrip antenna need to be coupled, and there is a feed. The feeding is required. So we can make from one antenna to multiple antenna. So for a communication, for example, Arduino is for IoT and IoT is for smart mobile phone 5G. Then 5G depends on the MIMO, multiple input, multiple output. That is nothing but a smart antenna. The microstrips antennas are the more suitable antennas. But there are also, we have seen for the IoT specification, LoRa is there, which is giving only some 10 kilobits per second of transmission. Nowadays, mesh is there, which is operating for 2.5 gigahertz, that is giving some 10 gigabits bits per second transmission. But for 5G, more than 10 gigabits of megabits of per second transmission is required, sir. For that, in addition to the LoRa, mesh, etc., the smart antennas and MIMO antennas are required for more suitability for IoT devices in future communication devices.
Sir, one more query, sir. I want
Yes,
to
sir.
know, sir. Actually, smart. I have heard about the isotropic antenna. So I want to know, ki, is the smart antenna is isotropic antenna, or I mean it radiates in all the omnidirectional, or it is a directional
Yes,
kind of antenna.
yes.
And second question,
Sir,
sir. Second question.
yes,
Sir. Sir, please tell.
yes.
Then I ask.
Yeah. Yes, isotropic antenna is basically a hypothesis. So it's a point source. It radiates the signals in omnidirectional. But in practical scenario, we use the mathematical model or all the technical aspects of isotropic antennas and omnidirectional antennas. But usually, in all communication devices, you consider a mobile communication, radar, etc. Microstrip antennas are used. They are just the mathematical model or the technical aspects of the isotropic antennas are taken, but isotropic are the point sources which radiates the signal in omnidirectional.
Yes, sir. And one last question, sir, by my side,
Yes,
because
sir.
I am so curious in this antenna field. Although my field is
Yes,
deep learning and machine learning and robotics especially, but I
yes,
am very interested in antenna because it is one of my favorite subject to when I am going to teach in my class. Sir, I want to know, sir, ki nowadays we have the 5G technology available. Sir,
yes, sir.
it is my matlab, main question to all the researchers or all the scientists, because we are human beings and we want to live peacefully. So my question is, sir, is the 5G
Yes,
radiation is actually radiation is very dangerous. I know that, sir. But is the
yes,
5G
sir.
generation 5G network radiation is harmful to us? Because in
Sir,
this
all ready. Yes, sir. Yes, sir. Yes, sir.
yes,
Yes, sir.
yes. In this context,
Yes,
many argument has been already, because scientists all they always say that because the radiation is around suppose such and such dB in decibel, so it will not
yes,
harm. But I know that, well, sir, we are not getting only the radiation from 5G network, but we are getting from Wi-Fi interference, from Zigbee interference, from TV radiations, and such kind of radiation in our homes daily. Yes, sir.
yes,
In the
sir.
future, I think there may be some there may be some devices or some kind of techniques कि people कहेंगे कि हमें अपने घर को सेव करना है with this harmful radiation, because
Yes,
for our genes, for our DNA, it is not good for the next
yes, sir.
generation. So
Yes,
सर मुझे ऐसा लगता है कि
absolutely,
इस फील्ड में
absolutely.
रिसर्च हाँ होगा सर इसमें आगे, और मुझे लगता है सर पर्टिकुलरली कि इट इज डेंजरस, बट
Yes,
maybe
yes,
sir
yes,
scientists are allowing कि 20 dB radiation is not harmful for humans. And sir, kindly tell
yes.
me about something about this.
Yes, sir. Here you pointed out a very good important question here in communication. All communication devices are communicating using electromagnetic waves. All electromagnetic rays are harmful and they are dangerous to the human beings and all creatures. But however, nowadays, due to advancement in the technology, particularly in the communication technology, non-ionized radiation is coming into picture, sir. Because of that only, the government has given permission to cellular towers being deployed in the cities also. We rarely find the deployment of the cellular towers in the cities near the school, near the hospitals, in the crowded areas earlier. But nowadays, the government has given a permission, and because of that, in your city also, in your area also, you can say that cellular towers are being deployed or installed near the schools also. It is because the non-ionized radiation, the radiation, the radiations which were earlier are now are not that of harmful to the any creature. So they brought the harmful level to the low level that it will not almost it will not affect to the human beings or any other because of non-ionization in the radiation. It is taken place. Sir, you are muted. You are muted.
Yes, sir. Yes, sir. Rohan Verma from HNB Gadwal University, Srinagar. He's an assistant professor
Yes,
there. He is
yes,
asking, can we use light transmit MIMO, multiple input, multiple output antenna in Arduino? Sir,
yes, sir.
this question is not,
Yes, sir. Usually light transmitting remotes are used in cellular towers, sir. Actually, how it works, actually how mobile communication works when, for example, when I'm picked a call, when I'm speaking, the speech signals go into the microphone. In the microphone, there are sensors are there and IC is there. They will convert the digital signal, and digital signals are in the zeros and one form. The signal are transmitted from the antenna, and these signals will go to the cellular towers, which comes in our area, where some the this what we told that type of MIMO antenna for that is light based MIMO antennas are there. They will convert this electrical signal into the electromagnetic wave, and that will go to the my friend cellular tower, and from my friend cellular tower to it will go to his mobile phone. However, this is not a good idea of using that for the light MIMO into the Arduinos, etc. This is the MIMO concepts is can be used only for the base station for the mobile communication development. For Arduino, etc., small antenna systems can be used, not in MIMO configurations. You're
yes,
muted,
sir.
sir. You're muted. Okay.
Yes, sir. Yes.
Okay.
The nice reply, nice answer by you, sir.
Okay.
So,
Thank you, sir.
any participants wants any questions? Please ask.
Else we can
Sir,
conclude the session, sir.
yes, sir. Yes, sir.
Yes. Okay.
Please,
Okay.
please conclude,
Okay.
sir.
Okay, thank you very much, sir. Thank you, Dr. Vishwanath, sir, the organizers of this IoT workshop, Atal FTP. I'm grateful to you for giving an opportunity to share my experience with you all with a very good audience and very good interaction. Thank you, one and all. Thank you, sir. Thank you very much.
At the end, I would like to also to conclude. Sir, we sincerely appreciate you for taking out the time from your busy schedule to provide us with such a valuable information. The seminar, the FDP earned a huge positive response. All thanks to your support, sir. I wish you great luck for all your future projects and look forward to meeting you soon. Thank you so much, sir.